hydrogen energy, and as we learned in detail yesterday night, he's now working in Bahrain.
So, good morning, everybody. I'm glad to be among you, and for that reason, I would like to thank the organizing committee for inviting me for this event and also for the conference. So, today I will talk about micro and nanostructured materials for hydrogen energy. So, I will talk about some microstructure, then we will move on to nanostructure. So, this is the outline of my presentation. I will give some brief introduction. Maybe some people are not familiar with some words or some concepts about hydrogen interaction with materials. Then I will talk about the main absorbing hydrogen materials. Then I will start with one microstructural system, which will be a very well-known system. Then I will talk about two nanomaterials. One based on magnesium, the other one based on carbon nanostructure. And finally, I will talk about new generation of batteries, which are called hydrogen and lithium batteries. So I just skip for this one because it's well known that due to the global warming, health problems, and oil price, this slide because it's increasing, but now it's stable around $50 US. So the search for renewable, clean, and sustainable energies is a very hot topic. So how we can store hydrogen? So hydrogen can be stored in three different ways. The first one is gas. Okay. So when you store hydrogen as a gas, it needs very high pressure, of course. So you need large tanks, and it's heavy for transportation. And that's why for cars it's very complex for transportation, and it's very hazardous, and there is a risk of explosion. Then if you go to the next one, which is more energetic or more dense in terms of capacity, so we have better storage capacity, but you need another energy to transform, for liquefaction, to transform hydrogen from gas into liquid, so it's another energy. And also there is leaks for long-term storage. Now, the third one, which I'm going to present in this talk, it's what we call solid storage. So, solid storage, that means hydrogen atoms are stored inside the material. In terms of crystal structure, it goes into interstices. I will show later. So, we call it solid storage, or what we call this kind of materials, metal hydrides. So, you can see this is a comparison between 3 or 4 types of energy hydrogen storage. So you can see compressed gas, 10,000 and 5,000. The density is about 40% or 40 per liter. If you go to liquid, it's double. Then if you choose, this one is a conventional metal hydride, and you can see it's almost twice of liquid storage. This is a basic metal hydride. If we use more advanced metal hydride, it will be maybe even more, maybe 20 times. I will show some examples later on. So now I will talk about the interaction of hydrogen with materials. There are different types of interaction. So the first one, we call it physisorption. Okay, so it's a surface effect. So the capacity is proportional to the specific, or what we call specific surface area, because it's physisorbed on the surface. But for this kind of storage, it's at low temperature, so it's not useful for room temperature application. And what kind of materials can be used for this application? Usually we have carbon nanostructure, of course I will present one of them, and metallo-organic frameworks. Now the second one, what we call chemical hydrides. So that means the hydrogen can be produced by chemical reactions. So we have hydrolysis, alcoholysis, and the last approach, which many people are working, is they use very complex hydride based on alkali metals, and through the decomposition you produce hydrogen. But the problem of this kind of reaction, they are not reversible. So just you produce hydrogen that you cannot be used, it's not reversible. I will show what's the difference later on again. Now the last one, what we call metal hydrides. This is the solid storage again. So we have different types of materials that have been studied for many years. So what we call conventional metal hydrides, it's based on metals, okay, or rare earth, whatever, transition metal. So this is the conventional, well-studied metal hydrides. And some of them, I would say, these two are already used as batteries for mobiles, for laptops, for rechargeable batteries, and also for electric cars. For instance, like Toyota and Sony, they use this kind of hydrides. So, and these are room temperature. So, that, as I said, they can be used for mobile applications and transportation. But the problem is the density is very low. So, we need to move to another type of hydrides. So, the second type is what we call light complex hydrides. They are based on alkali metal like sodium, aluminum, and boron. Okay. So this kind of hydride, they produce very high density. For this case, let's say if we have the hydrogen, how to say, capacity is about 1.5 in terms per element. For this one, it goes up to 10. So it's 10 times higher. You can see from when we move from. But these kind of hydrides are very stable. So if you want to make any reaction, it needs high temperature or high pressure. So again, it cannot be used at this stage for room temperature application. Okay, no. So why I want to move it from micro to nano? This is one of the reasons, because when we use it here, like these conventional materials, because they are micro scale, so usually we have a problem with the kinematics, because you want to charge and recharge your batteries very fast, of course, and the density also, and the thermodynamics, I will show in another slide, because there is a thermal effect we need to take into consideration. When you absorb hydrogen, when you intake or you release the hydrogen, there is some energy produced or absorbed. I'm going back, sorry. So we have, as I said, we have very high surface area, and we have fresh surfaces when you have nano, and there is also structural defects, and this will be useful to control the thermodynamics and the kinetics of this kind of reactions. So now, what is hydrogen solid storage, as I said? So you have hydrogen molecules. This is your material, of course. So you have hydrogen molecules. When they reach the surface, they are adsorbed as a molecules. That's why I said before, physisorption or adsorption. So they stay only on the surface. But due to after that, due to some, how to say, mechanism, I can explain later if you ask me. So they decompose, the hydrogen molecules, they decompose into atoms, and these atoms will dissolve into the structure. So they are safe. You can manipulate powders, and the hydrogen is inside. So they occupy usually interstitial sites. Okay. So the three main mechanisms, as I said, dissociation, adsorption on the surface, and diffusion into the bulk from the surface to the bulk. So what are the thermodynamics of this system? We need to understand for different applications. So this is when it starts to be at the surface. Then when it goes inside, then you reach the maximum amount of hydrogen that can go inside the materials. And this kind of mechanism, they are related or connected with Van 't Hoff equation, which is thermodynamics. So we have the pressure, the enthalpy, the temperature, and the hydrogen concentration, the number of atoms. And this kind of relationship, if you want to study metal hydrides or hydrogen storage, so you need to take into consideration this kind of relationship. But if I want to go in more details about the mechanism of interaction of hydrogen with materials, it has 7 steps. So some people who do some modeling, they go in more details. So you have mass transport, then chemisorption, as I said, or physisorption, dissociation, diffusion, transformation, because at the beginning you have metal with small amount of hydrogen, so we call it solid solution. Then as you increase the hydrogen content in the material, it becomes another phase, we call it hydride. So before you have metal, then after it becomes hydride. Now, what are the application of this kind of materials? So, of course, as I said, you can have the storage. Okay, so it can be used for electrochemical storage. So we have batteries for laptop and mobiles, and there are many computers or mobiles using nickel metal hydride batteries. You have fuel cells for electric cars and also for catalysis. This is kind of electrical. If you talk about hydrogen processing, so you can make purification, and also you can create or isotopes like deuterium and tritium, which are used for nuclear plant. You have thermal application, so you can have heat storage. I will show an example how to combine solar energy with hydrogen. It's another application also. And you have refrigeration. Now, if you go to Japan, I don't know if another country, they have refrigeration using Carnot cycle, because if you have absorption and desorption, as I said, one, you absorb hydrogen, heat, and you release heat. So if you combine two hydrides with different, how to say, thermodynamic properties, so you can, what is, for example, like AC. AC, it absorbs heat, and that's it becomes cold. That's like a vacuum. So when you absorb heat, so you create cold. So they have refrigeration using metal hydrides. Then what we call materials processing. So hydrogen also can be used as an element during, for example, to produce amorphous phases. So you have metal, if you interact with hydrogen, it becomes amorphous. So this is what we call phase transformation. And also, this is very good application they use for magnetic materials or hard magnetic materials, because so if you have bulk material, if you interact with hydrogen, it becomes powder. So you can see you transform a solid into powder. And they use it to improve the magnetic properties of magnets through this processing. They call it HDDR, I think. So it's when you interact, this is bulk, so it becomes with hydrogen interaction. This is neodymium-2 iron 14 boron. It's one known hard magnetic materials. When you interact with hydrogen, it decomposes into neodymium hydride, iron and boron, and small particles. But when you make it again, you remove hydrogen, it becomes again new materials with improved magnetic properties. And the last one is foams. You can have bulk materials when it interact with hydrogen. You make foams and you don't destroy the crystal structure. It's completely, how to say, you keep the same crystal structure, but just you transform the microstructure from solid into porous. And I give you one exciting project, example. Where is it? This one. Yes. So if I want to develop new materials for hydrogen, whatever the type of application, so I need to take into consideration these properties. So what is the capacity I want? What is the temperature and the temperature and pressure for different application? The heat, as I said, like for batteries, and that's why the battery is, because when you there is interaction between, especially for hydrogen batteries, nickel metal hydride batteries, during the release of hydrogen, there is absorption, and during the absorption, there is release of heat. So there is exothermic and endothermic reactions. And of course, the weight, if you have transportation or mobile application, or stationary application, and etc. Now, what are the main hydrogen materials? So this is the list of mainly used metal hydride. So this is what we call conventional hydrides. Then you have magnesium, then you have amorphous, you have quasi-crystals, you have carbon nanostructure, nanofibers, nanotubes, and now graphene. You have complex metal hydrides, thin film. I will give an example about this, and how the hydrogen interaction with materials can change the magnetic and also, how to say, the optical. Now I work also on another field about spintronic materials. So you have a semiconductor like zinc oxide or cadmium oxide, whatever. If you make interaction of this oxide with hydrogen, so you can induce a ferromagnetic behavior, and we published this in RCS Advances, and we got good citation. So the interaction of hydrogen can change the physical properties of your materials. And I will show a good example. And you have also zeolites, and this is what I show, how you switch the optical properties of materials with only hydrogen. And also, as I said, more. So this is a good example, because as I said before, the interaction of hydrogen with the rare earth, if you have a solid like this, a bulk material, if you bring hydrogen in a gas, it will become powder. So we cannot access the optical properties of rare earths before. So what they did, so they make a thin film of yttrium and they cover it what? With platinum. Okay, yeah, palladium, sorry, I said palladium. So you can see this is a thin film of rare earth, yttrium, 500 nanometer, and we cover with palladium. Why? I said because the interaction of hydrogen will destroy the material, the bulk. It becomes powder. So you cannot access the optical property. So what they did, they put a thin layer of palladium, because palladium absorbs hydrogen, so it's just a layer to cover. So the hydrogen can penetrate or interact with the second layer. And you can see now how you can change from metallic into highly transparent. Because this is only yttrium metal, and this is yttrium hydride after interaction. So this is what we call switchable optical properties due to the interaction with hydrogen. Now I will move. This is an example for students, because the processing and manufacturing enter to the materials performance. So I always focus on this. So I want, if I produce a material, the method I choose, or the processing, or the pre-treatment, or the post-treatment, sorry, it will affect the crystal structure, so the crystallography, then the microstructure, shape, size, texture, defects, etc. Then this will affect, as I said, the properties, and we have direct influence or effect on the performance of your material. Now, I will start with the micro system. So this is a quaternary system. So we prepare by conventional melting technique. So zirconium, why I'm interested in this compound? Because it has two types of crystal structure. You have a cubic and hexagonal. Okay, so since I said the hydrogen is inside the crystal structure, so if you change from cubic to hexagonal, you don't have the same number of interstitial sites. So if you want more hydrogen, maybe it's more convenient to work with hexagonal. You have more sites, and maybe for cubic you have less sites. So this is interesting also in terms of crystallography, because I'm crystallography by formation. But I don't want to go in details, but if you ask me, I can explain later on. So we did what we call phase map. So depending on the composition, we can obtain cubic or hexagonal, and also we form a secondary phases due to the instability of some of what we call zirconium nickel 2 and titanium nickel 2. Please remind me about the time, because it's 25. So you can see that this what we call phase map. So then after that, we did hydrogen interaction. So what does it mean? If you have a system, you introduce hydrogen, so you increase the hydrogen pressure, and this is the amount of hydrogen adsorbed per meter. Okay. So from this we can calculate the hydrogen capacity or electrochemical capacity. I will show you an example. So if I have one hydrogen atom per meter, for my system, this one, I can expect about 350, if I'm not wrong, something like this. The hydrogen capacity for batteries, just to go quickly. I can't remember the numbers. Yes, you can see here. So this is the discharge capacity I expect to get, 300 milliamps hour per gal. So now I come back again. So this is interesting because for PhD, of course, we need to do some crystal, some basic concept. So I use it, as I said, I have two systems, cubic and hexagonal. Which parameter I control to change this cubic? So So I did some theoretical investigation, and I can see that depending on the element, if I replace zirconium by molybdenum or vanadium, I stabilize the cubic phase. Okay, you can see here. But if I put another transition metal from manganese, etc., I stabilize the hexagonal. So this is interesting for me that I can play with the substitution or with the chemical composition to change from cubic to hexagonal. So this will affect, of course, the hydrogen storage capacity. Again, when I put these elements, how this affect my interaction with hydrogen? Is it good or bad? So again, I find that these elements favor to have less stable hydride. What does it mean, less stable? It means you can release hydrogen easily. If you put molybdenum and vanadium, they become more stable. That means you cannot release hydrogen. So this is very interesting because it's a prediction for me. I don't want to imagine how many elements I have and how many composition I need to prepare. So to use some kind of modeling, like DFT, I will say also density functional theory, or this sample method. So before I ask to prepare many samples in terms of time consuming and expensive, so I can make a prediction where to go. So now I don't need to go in this direction, I prefer to do with nickel. And that's why I choose nickel in my center, because I did this investigation before. So now I choose this composition among the others, because I did a lot of work. So we found that this composition is very suitable for nickel metal hydride batteries for mobile phones and laptops. It has a reversible capacity of 0.5. Okay, the kinetics is faster, so we can charge and discharge very quickly. And we want to understand the mechanism as a physics why. So we did. I was lucky to be in Grenoble, so we did some neutron diffraction, in situ neutron diffraction. So this is a Rietveld analysis to check that the chemical composition. This is very powerful technique for phase identification and how to say phase composition. So we know that we have a matrix of 60% of my phase. This is a secondary phase and 5% of chromium. Now I want to do in situ reaction. That means I put my sample under hydrogen atmosphere and I use neutron diffraction. So we can see that with increasing hydrogen pressure, sorry here, so this is a recorded diagram. When I go from here to here, I increase the hydrogen pressure. So you can see at the beginning, this is these two peaks belongs to the cubic. This star, 3 stars peaks belongs to the secondary phase, which is zirconium 7, nickel 10. So during the hydrogen interaction, you can see that these peaks disappear. Why? So that means they are crystalline. When they disappear, they become amorphous. As I said before, the interaction of hydrogen can change the crystalline phase. So it becomes amorphous. And then the peaks of this phase shift to lower angle. What does it mean in terms of X-ray diffraction? That means there is expansion of the lattice. Why? Because hydrogen go inside. So when you have hydrogen go inside, you have lattice expansion. And this is very important for me, because if I want to design a battery, imagine I make a battery like this. Then after hydrogen absorption, it increases. So you have the volume. When you make applications, the expansion of volume you need to know. So when you design a tank for hydrogen storage or a battery, you need to know this volume expansion. So imagine, I will show you the expansion of volume. Look, imagine 30%. So when you design a battery or tank, you need to know that it like increased by 30%, reduced by 30%. So this fluctuation, how you are going to do in terms of application. So you need to access this kind of data for different applications. And can you imagine it can reach up to 20% of volume change for some compounds. 20% of volume change. It's not easy. So you need to consider this kind of application. But what is interesting for me is this one. So it means, what is this? This is for the secondary phase. This is zirconium 7 nickel 10. It means you can put hydrogen until to 2%. After that, you destroy the crystal structure. Why? Because you have, as I said, volume expansion. That means the interatomic distance increases. That means after you lose this short ordering in terms of crystal structure. So as a physicist, it's very important for me. So this compound, after 2%, you lose the structure. Now, again, we want to understand the reverse mechanism. I told you because when you're charging and discharging, how many times? 1,000. So for me, I need to understand what's happening during charging and discharging process for a different application. So I charge, one is crystalline, one is amorphous. Okay, now what I discharge, what will happen? Shall I come back to the initial or not? So now when I remove hydrogen, we can see that the main phase release hydrogen very quickly within, you can see. I can follow the lattice parameter here, and you can see it releases hydrogen very fast, like 1 or 2 minutes. But where are the peaks of the main phase? They doesn't appear. That means it remains amorphous. It cannot come back to crystalline phase. Only the first phase. So what I did what we call crystallization process. So I increased the temperature, and I can find that zirconium 7 nickel 10 can recrystallize at 100 Celsius. So this is what we did in terms of in situ reactions. And this is the mechanism we propose. Now, I did some electrochemical testing, charging and discharging, because I want to use for as batteries. So we did this charge, and we obtained that, you can see that this is as prepared. We can reach up to 300. This is why when the first time you use the battery, they ask you to charge, fully charge it, you know. Because if you don't full charge, you cannot reuse. So this is for safety. They always ask you to overnight charge your batteries. And you should not discharge completely, it's dangerous also. So we have a range. So you can reach 100, but you cannot go to 0, it's not good. So if you leave it at 10%, it's not good to be safe. So I think I need to go because I have other... now I move it from this system. As I said, these conventional materials, they have low capacity, which is 1.5. Now, because especially for electric cars, when you charge your battery, you want to stay, not each half hour you need to charge your battery. So you need to run maybe for 2 hours, 3 hours. So we want to use other compounds, they have higher capacity. So if you use magnesium hydride, it has 7.6%. So you can see now we move it 4 times. And magnesium to nickel 3.8, which is that. Okay. But the problem of these compounds, they are very stable. It means you cannot use for room temperature application because the decomposition is 350 and the kinetics is very low. So how to overcome this? In terms of material science, you have different mechanisms. You can make mechanical milling, it means you reduce the size, okay, to the nanoscale. You can make doping or catalyst. What's the difference between doping and catalyst? I was asking the student yesterday, because doping means you go inside the structure. Catalyst means it stays outside. Okay, they can have the same role, but it's not the same mechanism of interaction or mechanism of interaction. And the substitution is another issue. So we have doping, you have catalyst, and you have substitution. So now we did magnesium hydride. We tried to mix with transition metal. So we choose this kind of element. So before that, before I prepared this system, what we did DFT calculation, density function theory calculation, again to predict which element will give me the best properties. So we did a supercell. Of course, this is the calculation. So what are our results? This is our results. So you remember the first equation I told you is the relationship between pressure, enthalpy, temperature, and number of hydrogen atoms. So this is the enthalpy. So this is magnesium hydride, is minus 76. That means it's very stable. We cannot release hydrogen. That's why we need to heat the material to release the hydrogen up to 350. But I cannot use for electric cars. Okay. So how to destabilize? So you can see when I mix magnesium hydride with aluminium, platinum, etc. So I can modify the enthalpy. So you can see now which one is more stable as I decrease. So for me, I noticed that iron and nickel destabilize this magnesium hydride. Is it true or not? This is from calculation, DFT calculation. So I come back to the experiment. I always make mistake of this. So we prepared this sample by mechanical milling. So we mixed magnesium hydride with 8% of metal, and we did mechanical milling, and this is what we obtained. So at the end, some element they dissolve. Why? Because of the atomic radius, some kind of electronegativity. There are many parameters to control the diffusion of elements into the crystal substrate. So we form different, some solid solutions, and we form a secondary phase. For me, it's good because I showed before that to form a secondary phase, sometimes single phase is not good. Okay? So the formation of secondary phase is very beneficial for me. Okay, so it helps to improve the kinetics. So now, what is the thermodynamics of the system? So I did what we call thermogravimetric analysis. So I made the hydrogenation at 300 Celsius. So you can see, as received, when I buy magnesium hydride, you can see it doesn't release hydrogen, even at 300. That's why I said it's very stable, and the kinetics is very slow. You cannot release. So to get better comparison, I mean pure magnesium hydride and the same condition. Again, magnesium hydride release very, very slow. Now, you can see now when I mix with another metal, so the kinetics completely change. So which one is the best? Again, where is it? Nickel. If you check nickel here. So the best element is nickel, so we confirm our theoretical calculation. So nickel is very, and also because nickel is well known as a catalyst for hydrogen dissociation. That's why we use. Okay, now then we move it to another system, what we call carbon nanostructure. So you have different types of carbon, but for us, we wanted to use carbon nanofibers. And why we use carbon nanofibers? So because carbon nanofibers, we have two types, what we call platelet, okay, that means the layers of carbon are along C-axis, and we have what we call herringbone. Herringbone, it means this kind, it's like cones, it's like in this way. Again, C-axis, but it's cone. Okay. Why we are interested in this? Because the distance between the layers, so the distance between the layers, it's about 289. So we expect that the hydrogen can be intercalated between the layers. Okay, and what is the mechanism? Of course, it's physisorption or adsorption. So as I said, they don't hear me? Because of me. So which one I should use? Yeah, but the question, you can repeat the slides. Okay, so I can change the. So, as I said, why we are interested in carbon nanofibers, because the distance between carbon layers is about 335 angstrom, and the molecular diameter of hydrogen, the molecular diameter of hydrogen molecules is 289. So we expect from this that hydrogen can be intercalated between carbon layers. And at that time, we see many papers publishing theoretical investigation about, again, DFT calculation, that carbon nanofibers can absorb or physisorb, whatever. We don't know the mechanism yet at that time. About 60%. This is huge. I didn't believe this. Then we make literature review. Please, can you? Yes. So when we check the literature review, some people they report 1 to 2 weight% of hydrogen. Other people they say 10 weight%. This is experimental. Theoretical they said 60. So we need to analyze this data before starting. So with my student, PhD student, I said let's analyze. So why this high discrepancy between the results? What are the reasons? So I need to understand why. So first, some paper they measure using volumetric. So what does it mean, volumetric? That means if you have a material, you have, let's say, 10 bars of hydrogen. After reaction, what is the change of the pressure? If it absorbs, that means the partial pressure of hydrogen will be reduced. So, and you calculate according to the volume, and you using very complex equations. So it's approximation. The second one is gravimetric. So this is very good, it's very sensitive. But it depends also on the sensitivity of the balance. If you use a micro balance, that's good. If you have 0.1 microgram of sensitivity, this is very but the problem of gravimetric, you cannot use high pressure. So it's another problem. The second parameter is the mass of the powder. So if you use 10 milligram or 50 milligram or 100 milligram, is it the same accuracy? No. So that's why we have discrepancy between the values. Now, the third parameter is the accuracy of hydrogen transducer. As we were talking yesterday about the girl who presented about glass gel based on germanium, something like that. The purity of elements has an effect. So, the type of transducer and the type of purity of hydrogen. As I said, 5N already is very expensive hydrogen. But do you think it's pure? I will give you an example. What happened? We did one test. We bring normal hydrogen and we interact with materials. I noticed, oh, I find my carbon nanophase absorb hydrogen. I was happy. My boss said, oh, very good. Then we changed the type of purity. We use it 5N. We find less hydrogen capacity. Oh, this is question mark. Why? Then what we did, to be sure, we use what we call, I will show in the system later, it's why we use liquid nitrogen trap. When you say the purity of hydrogen, 99, what does it mean 1%? Do you know what is 1%? It's humidity. And the humidity can be physisorbed on carbon nanofibers. It's very active. So it will be physisorbed. So what you measure, it's not hydrogen capacity or hydrogen adsorbed. It's finally humidity. It's adsorbed, even 5N. And I did my test. So I put, I make U-tube like this, and I flow, and I have a tank of liquid nitrogen. So when I flow, I can hear bubbling. What is bubbling? That means the liquid nitrogen, when you, the hydrogen, when it flows through the liquid nitrogen, it traps all the humidity. So people who work with hydrogen or other gases, to avoid this kind of humidity, because it interacts with your samples, and you need to use this kind of technique. Please, yes, yes. So now we move to the synthesis. How many times I have? How many? 15 minutes?
Yes,
okay, I need to speed up, yeah. So we prepare different type of carbon using different catalysts. You can see that we have different parameters to control. So, next one please. So, for us, we use CVD technique, it's very simple. Then we use two types. This is the first, I think we published these two papers in carbon, because it was the first, maybe not the first, but we try to use oxide as catalyst, because for carbon, usually they use metal or metal alloys. Okay, so we use oxides based on metal. Then we vary the hydrogen to C2H4 ratio. We fix the time and we vary the temperature. Next one. So we did X-ray diffraction, of course, but it doesn't tell you what kind. You can only see the peak of carbon, but you don't know if it's carbon nanofibers, nanotubes, whatever. You know. And we can see that we have the formation of nickel, metal, or nickel carbide. Imagine at 800 you form nickel carbide. But for me, as a material scientist, it's very surprising, because carbides, metal carbides, are usually formed at very high temperature. But our maximum temperature is only 800. That means, again, we can use hydrogen. You can see the hydrogen to produce other materials at very low temperature. This is the benefits of using hydrogen. Carbide, you can check in the literature. All carbide are formed at very high temperature. Okay, next one please. So this is what we obtained from X-ray diffraction. So we obtained nickel around 500, nickel carbide at lower temperature. Imagine, 400 Celsius, you form nickel carbide. And we have high crystallinity above 600. Next one please. So we did TEM, and we can notice different approaches. So, next one. Again, this is just, I can show you later if you are interested. Next one, please. Yes, this is what I am interested in. Because I want to know the type of carbon nanostructure I have. So we do TEM, but we do also selected area diffraction, SAD. So from this, if I make selected diffraction of this carbon at 400, what I can see 4 spots. What does it mean 4 spots? It means I have herringbone structure. So it's not platelet, it's not nanofibers, but it's herringbone. If I go to 500, I can have, you can see 2 spots, but they are elongated. What does it mean? That means I have aligned carbon layers, but they have so many defects. Why they are elongated? Because there is some amorphous carbon. Okay. Now, if I go to high 100, you can see the spots are well defined, and because they have more crystalline carbon nanofibers. So you can see with TM we can know or detect the type of nanostructure we form. Next one. So we did phase map. So you can see depending on the hydrogen content or ratio between hydrogen and C2H4 and the temperature, we form different type of carbon. Multi-wall, nanotubes, platelet, herringbone, and encapsulated carbon. So this is the phase map. So for carbon. So this is for iron catalyst. The next one, this is the one for nickel catalyst. Okay. So here you will obtain CNT. So for the other one, multi-wall or single wall, it's different completely. So depending, as I said, on the catalyst, temperature, and hydrogen content. Next one. Now, so as I said, for some types of materials, the absorption, the reaction of hydrogen can be by physisorption. That's why I need to measure the surface area. Okay. So this is the diameter. This is the type of carbon we form, and this is the surface area. Next one. So we did high resolution TEM. Maybe it's not clear on the picture, but this is the layers. But what we see on the surface, there is what we call capping. It means the layers, they close up. So if I want to intercalate hydrogen between the layers, it's not possible because it's closed. One. Second thing, we form amorphous carbon. I did SAD again because if you make a selected area diffraction, you can see a continuous ring. If you have a continuous ring, that means you have amorphous carbon on the edge of carbon of your tubes. So this is very common for carbon nanostructure, especially nanotubes, multi-wall or single wall. You always, in some case, you have always an amorphous layer on the edges. So that's why people, to make functional carbon nanotubes, they need to make surface treatment, either using reflux treatment or other methods. Next one. So we need, so for our case, we cannot make hydrogen absorption because we need to make surface treatment. So we did oxidation. Why? Because I want to eat the surface. It's like to cut. If I have a scissors, I can cut. So I need to make oxidation. Then the next one, hydrogen reduction. Why? Because I want to remove the oxygen. Because if I have oxygen species, it will make interaction with hydrogen and I produce water. I don't need. I need to have free oxygen. Then the next one, okay, now we did XPS because we want to control, we need to know what we have on the surface. So you can see now when we prepare, as prepared, we have 0.8% of oxygen. When we make a reflux treatment, it's efficient, but it produces a lot of oxygen species on the surface. For me, I don't like. So when we do CO2 treatment, we have oxygen. Then when we do finally hydrogen reduction, we have the lowest hydrogen content. Now, next one. So now this is the system. It's homemade. It's not easy to buy system. Imagine this system. It works up. Look how, what is the pressure? 100 bars. What is the temperature? 1000 Celsius. It's like explosive, you know. So we need to be very, very, very careful. And we need to check all the leaks. Because any small leak, that means we measure with velometric. That means the pressure change. That means if I have a leak, what does it mean? I can measure hydrogen absorption, but finally it's not true, it's a leak. So it's false reading. So, and we did, to avoid this problem also, we said differential system. If some people, they use only one part. So if you have a leak, you measure the leak. But when you have a differential system, you measure, it's like you have a reference and your material. So you have reference and my material. So I measure the difference in pressure. So it's more precise. I try to improve the system as much as I can to have more accurate data. Then we did measurements. Next one, please. So this is the result. So we did at 30 Celsius under 100 bars. So this is the results of hydrogen. So carbon nanofibers doesn't absorb hydrogen. But as I said, many people they publish. But most of the results, honestly, this is my opinion, as an expert of hydrogen also, for 30 years almost, so most of them are wrong because for several reasons. Then after CO2 treatment, you can see that it becomes more active. Hydrogen reduction, no difference. Now what we did, decorated carbon nanofibers with 5% of palladium, so we can reach 129, okay? Why? The palladium, as you remember, for thin film, we put also a layer of palladium. It's very catalytic for hydrogen. Then we compare with Maxorb. Maxorb is a very well-known carbon material, and it has very high surface area. So, what is the mechanism for me? If I compare Maxorb with my sample, this one, Maxorb, as I said, if it's physisorb, it means it's interaction with surface. So it depends on the surface area. That means I should find lower than this because my surface area is only 50 or 100 and this is 3000. So my sample should have less. So the mechanism of my adsorbed hydrogen is not clear now. Next one, now I move to the new generation of batteries because if people are working on lithium or hydrogen, whatever, there were always competition between lithium batteries, even in the market, and companies they are competing between lithium batteries and nickel metal hydride batteries, either for mobile or laptops and also for cars. Now, this is the first example demonstrated by my colleagues in France. So they make a combination between lithium and hydrogen. Okay, so if you have a magnesium hydride, you have lithium, and you have, so you can hydrogen be released and interact with hydrogen, with lithium, and you have lithium, hydrogen, and magnesium. I don't know people if are known, imagine the capacity, how much? 1,500. It's very, very high. And they publish this in Nature. Okay, now I worked on this system. Next one, please. So I work on nickel titanium. People, they say, oh, this is shape memory alloy. Yes, it's a shape memory alloy. But it also can absorb hydrogen. Why? Because titanium can absorb hydrogen. And nickel is very well known as catalyst. So we did mechanical milling. Next one, please. Then we can see that by mixing titanium nickel under hydrogen, I get amorphous phase. This is very nice for me. Next one. So we did SEM. Again, next one. So we want to do TEM also. So we find that, you see this ring, it confirms the previous one, please, just one. Previous one. Previous one again. Yes, you can see this is amorphous. As I said, TEM will help you also to know if it's crystalline or amorphous. Now we come back. Yes, you can see, no, previous one. Yes, you can see the continuous ring. Why? Because nickel titanium becomes amorphous. What are the 4 spots? So you need to be very careful. So the 4 spots belongs to iron because it's contamination with the milling tools. So we have very nanocrystalline iron, and we can detect with EDS, and amorphous. So we have amorphous matrix of nickel titanium with nano clusters of iron on the surface of nickel titanium, which is very useful for us. Next one, please. Now we did electrochemical testing. So you can see alpha nickel titanium hydride plus lithium, and we obtain alpha nickel titanium plus lithium hydrogen. So now, what is the theoretical capacity of this compound? I think it's 346. But for our case, we obtained only 251. And we explain this, as I explained already in the first one, that amorphous phases doesn't release all the hydrogen. So it's very consistent. You can see always is the same story. 5 minutes, okay, that's good, yeah. So now we did DFT calculation again, because it's a support for our, if you want to publish in good journals, so you need to add some modeling. So we did DFT calculations, and we obtained very good correlation between our results. So if we come back to the previous one, please, previous slide. Yes, So you can see the plateau of reaction is around 0.4. Now next one, and from 396, and from the 0.4, sorry, and from DFT calculation we find the same plateau. So we can predict, our calculation. Next one now. Now this is my future project. Now I'm working with my colleagues. It's how to combine energy, solar energy with hydrogen also. So if you imagine, as I said, the interaction of hydrogen with metal, it's exothermic, and if you reverse the reaction, it's endothermic. Okay. So next one. So imagine you have a CSP, so you can produce a lot of sun. You can produce a lot of heat. Where do you store this heat? So we say, okay. So if you take this heat and you have a metal hydride tank, okay, an alloy or metal that absorb hydrogen. So if I have a metal hydride inside the tank, so if I bring this heat, I will produce metal and hydrogen. And this hydrogen, I will store it in another bottle, separately. And I close, okay? Then, if I want to get this heat back, what I need to do, I just open the bottle of hydrogen. It comes to interact with material inside, and I will get the same amount of heat released. So this can be used for mobile application, for housing, etc. And they are using it already. So, next one. Okay, now the conclusions. So, as you can see, I showed that we have different systems. I studied from different type of kind of materials. Now, in my work, always I try to do DFT calculation to predict. Next one, please. Yes, next. Yes. Now we are working on, as I said, zirconium copper. Why? Because I showed in my previous system, in first system, that the interaction of zirconium nickel or zirconium copper with hydrogen makes amorphous. And for some application, I think some people, if they work on material science, amorphous phases, they have sometimes higher mechanical properties, for instance, than crystalline materials. Then we work on this system, magnesium-7 system. We work on, as I said, nickel titanium, and this is also another system with layered, it's like carbon again, it's layered structure, and we try to intercalate hydrogen between these kind of layers. Next one. Okay, finally, thank you very much. This is my collaborators in my all this work. Okay, I should thank them also again. Thank you.
Thank you very much. Very powerful presentation. Now the floor is open for discussion, comments, questions. Okay. I have a few, but you think. I give you time to think. For instance, could you comment on the possibilities of composite materials, for instance, including carbon tubes or other fillers, for physisorption of hydrogen on the surface, but also for small possibility of diffusive penetration inside the bulk?
Yes, yes, of course you can. Because depending on what you want, you can choose the right materials, So if you, some people now, they are working on hydrogen sensors, by the way. It's the same. Because they want to, hydrogen sensors are very useful for different applications, especially for industries, So they use in that case, you don't need large amount. Just you need to detect the hydrogen, but you need very sensitive. So what you need, it's not the amount. It's just you need to select very fast kinetics. So they combine some kind of composites, like they combine lanthanum nickel 5, because it has very fast kinetics, and carbon.
But what about polymeric matrices?
Like metal organic frameworks. Yes, they are doing. But again, these kind of materials, they exist, but you need to go to low temperature, 70 K. Mm-hmm. So maybe if you make composites, as you said, if you combine metal from MOFs with maybe another metal, you can reach maybe low temperature, but it's very complex.
Did you think of some questions?
Yes, please.
Yeah. Just to see why you can write that delta G is about delta E.
Sorry, can you repeat?
In one of your slides,
yes,
you wrote that delta G is about delta E.
Delta H?
Delta G. Delta G, I don't know how to say.
The free energy.
Yes. Why you can write this?
Delta H I calculate. One of them.
No. you wrote delta G is about when you calculate the potential. Of course, you need delta G.
Oh, yes,
You
yes,
write
yes.
delta G.
Oh, yes, 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 I remember.
Equal to delta E. Why you can write this?
Yes, because I need to know the thermodynamics. So delta G is delta H minus T delta S.
Yes.
Delta S is the entropy is fixed, but you know that because this system depends on the temperature. So I cannot use only delta H.
No, you have to use delta G.
Yes.
Once you wrote that, I know that from your calculation, maybe you don't calculate the vibrations of the system, and so
No,
you have
no, we
just
don't.
delta E.
Yes.
But in principle, you can calculate also delta G.
From DFT calculation, we
Yes.
access only from DFT calculation. Not how to
In
say.
principle, you can calculate
Yes,
vibrations, and so you have also the entropic
Yes, entropy.
contribution, and so you can calculate delta G,
Yes.
not just delta E.
Yes.
System.
Yeah, I know, of course. Because people, they use in molecular dynamics, they calculate. But for us, because it's metals, maybe they don't use this vibration. Maybe it's not, maybe it's insignificant.
I think we need to deepen this.
Okay.
Can I call the floor for one more question? Students.
Students, why? Yes, we are here for you.
Okay, so
You can ask any question, yes.
Passive. Okay, I'll ask one last comment, if
Yes,
you may.
please.
Do you see any role in transition metal decalcogenide-based materials? I don't know, for instance, molybdenum disulfide, nanotubes, or titanium disulfide, nanotube for the hydrogen absorption?
Storage, no. For storage, no. I said you can't change the properties by hydrogen. I did because I work on zinc oxide. It's a semiconductor and it's paramagnetic. So when I interact with hydrogen, it becomes completely ferromagnetic, which is new. So this is a new application, what we call spintronic. It's another application.
Also on disulfide?
Yeah, it can be. That's why, yes, of course. You can change the physical properties.
Okay, we thank you again.